Sounds good. So yeah, I mean, as was mentioned a little bit earlier, yeah, the paper was a bit short, and it also, I mean, I'm not super familiar with hardware hardware components of networking, computer networking, so had to read a bit on we'll have to read a bit on the architecture and basically what a NIC was, and generally how some of this worked, and all the other stuff that they referenced. But essentially, right, the thesis of the paper is, or well, what they start with is by giving you an overview of what is currently offered in as a cloud service, right? And they argue, well, we generally have generic compute, which we can think of as VMs, or serverless in some sense, where you can just execute programs, and then you have storage resources where you can basically save stuff. And then they also say, well, and there are some specialized accelerators like GPUs and FPGAs that are offered by cloud providers. And they argue, well, and that's basically it. But recently there has been programmable networking devices that allow that have in-network switches or at-host smart NICs, where you can basically write custom code in them, and then basically achieve different types of behaviors. And I actually, this when in the Slack message where they asked what other message might be, what other papers we should read, maybe we could get some ideas from this one. I glanced at Eris and No Paxos, but basically what they're arguing is that if you're able to, if you're able to leverage the programmability of these devices, you can actually achieve certain innovations that improve performance and well, basically just give us generally good things, right? For example, Eris is a concurrency control system that, well, I glanced over the paper, but basically allows you to execute distributed transactions. No Paxos, well, they claim that with using by being able to program the network, you're basically able to avoid Paxos with little overhead, and you because you rely on the ordering of how messages arrive on the network layer. And I didn't get a chance to look at the other Netcache or NetChain, but I think it's definitely worth looking into those papers if you want to learn more. But basically, the gist of it is that with these programmable devices, we can do really cool things. And the question is like, well, why are these things not offered as a cloud service? And the problem that basically, well, the conclusion is that it needs multi-tenancy support. And multi-tenancy support essentially means that multiple programs should be able to, multi-tenancy basically means that it should be shared, right? That we can share this single resource among multiple programs, and therefore, if you're not able to do that, well, then you cannot really offer it as a cloud service, because then the whole point of cloud is that you can give a fraction of a resource to someone and they can do whatever they want. And there are lots of benefits from this, right? From the provider aspect, right? And providers being all these huge cloud services, they can improve resource utilizations, because one single application cannot really consume all of the hardware resources. And then sometimes there are different requirements for each of these programs, and being able to offer multi-tenancy support will help here. And then from the tenants aspect, well, you can enable innovation, right? Being able to program these switches or NICs basically will allow more programs and different types of programs to be created. And you can also test things without impacting the basic network functionality. And then they describe, well, what are the requirements to enable multi-tenancy for these programmable devices? Well, they say, well, we need resource efficiency, which means that you should be able to allocate a specific portion of this hardware component to a tenant. And when you do it, it shouldn't really it shouldn't add too much overhead that sharing should not add too much overhead to the program itself, right? Because then otherwise you would be wasting resources in the multi-tenancy, right? So the requirement is that there should be little overhead when you're sharing these things, and then there should be isolation. And by isolation, they specifically mean that the performance, once you allocate a specific portion of the device to a program, they should be able to use everything that has been allocated to them, and their usage should never affect any other tenant or any other program that's also sharing the programmable switch or the programmable device. So those are the two requirements, right? There's little overhead and you have isolation. And they propose a compile time and runtime solution. It's a combination of two programs as a way of achieving multi-tenancy for the programmable devices. So they first, so this diagram, before going into explaining the solution, they give a bit of an overview on how these network devices work first, right? So that we're able to talk a little bit better about the solution. And generally, let me see if I can, sorry, let me see if I wanted to, right? So we first, right? So they generally have a parser. They generally start with a parser that extracts things such as the headers. It reads, I mean, most of them read the standard headers, starting with Ethernet, then IP, then TCP, UDP, ICMP, the general protocols. Then it's usually followed by an ingress pipeline, where you basically have matchers to certain rules. So you can say, well, if we're using TCP, then apply this action. Or if it's a UDP packet, then apply this other action. Then they're passed later on to queues, and then there's an egress pipeline that is then forwarded either into the computer, into the VM or outside the VM. And they also give a bit of a, they dive a little bit deeper too on the egress pipeline. So to give you a sense, they say, okay, well, you have all of your headers here, and you're able, you have also the stateful memory where you generally store part of the information that you extract from the headers. And these red diagrams, these red squares that they see, they're basically then matching this logical explanation of the programmable device to the hardware containers. So they're basically telling you that these headers are usually stored in a PHV container. This is packet header vector container. The stateful memory that you have available to you, it's basically stored in registers. And then the circuit is equivalent to action units. And then the matching is basically used with exact match crossbars or ternary match crossbars. So they try to explain essentially the hardware components that match to this sort of logical software components that are of basically the whole pipeline of packet flow. Are there any questions regarding how these programmable devices work?
All good.
Okay. Okay, so right, so then what they say, now that they've explained the pipeline, they say, well, you have these devices, and they basically explain a little bit of the different types of devices. They have various types of hardware resources, and the use of those resources is decided at compile time. And generally, all of these all of these devices, even the most programmable ones, have very limited runtime support. as mentioned earlier, the hardware wirings are decided during compile time, so you cannot really move that at runtime. There's also no temporal scheduling like CPU or NPU scheduling, and there's also no special reconfiguration like in FPGA. So it's very limited what you can do in the runtime, and as we'll see moving forward, essentially basically the only thing that you can modify at runtime is the stateful memory of the program, and they're actually kind of clever about how they manage this. So again, the takeaway here is hardware resources are compiled are decided during compile time, and then during runtime, really the only thing we can play with is stateful memory. So they mentioned that their solution is a hybrid compile time and runtime solution. And the compile time program linker targets generic resources like SRAM and TCAM, and the action units, essentially the stuff that we mentioned earlier that is part of the flow. And then the runtime solution is essentially just a runtime memory allocator. It targets a stateful memory that's available to the whole device. Okay, so sorry, I'm trying to move the menu. I need to drag it. Okay, so we start off with the tenants, which are the programs that are basically defining or writing the programs for these programmable switches, and they're basically compiled along with a system program defined over here, and they all go into a compile time linker. We have a resource sharing policy that it's basically the one that decides how much each tenant is allowed to use, and they actually don't really. One of the limitations of this paper is that they don't actually give you a specific resource sharing policy. They suggest several ones, right? They say you could use some dominant sharing utilization in which you basically try to allocate based on usage. I'm sure you could use a waterfall algorithm here as well, or they could say, well, you do a pay-as-you-go. They basically say it's up to the implementer to decide what resource sharing policy they want to specify for each tenant. The linker also has a resource usage checker, which basically verifies that the tenants stay within their limit, and then the program linker that puts everything together, and you end up getting a jumbo program. At runtime, you essentially have a control plane and a data plane. The table entry handler here contains a lot of the configuration, and tenants are able to submit requests via gRPC to the control plane if they want to request an adjustment or they want to request more resources based on usage. Then what happens is well, they describe several stages, but then in one of the stages, they basically the programs report back to their usage to the utility calculator. So based on how much everyone is using, this reporting is sent to a reallocation problem solver that takes into account the requests that are sent from the tenants to then basically come up with a new configuration and basically a new allocator of memory, and then it sends it back to the data plane for it to be implemented. And that's essentially how we're able to modify during runtime the memory allocation of each tenant. Are there any questions? Okay. So as they say in part of the programs, the goals of the compile time linker is to restrict the resource usage, essentially being able to at compile time define what specific resources can each tenant use. and also provide isolation, right? They want to ensure that the tenant program does not interfere with others. It also makes sure that there's no infinite packet resubmitting, in which they could overcome some of these limitations, and that there's no loop forwarding configuration. Then they go into some more detail as to how this works. Essentially, and basically it talks about the interaction between the system program and the tenant programs. And basically, for example, on the parser side, the systems program extracts the common headers, the ones that for the most common protocols. So you could see, that this set of headers are handled by the system. And then after it extracts the most common headers, then it's passed on to the tenant programs, which is identified by a virtual ID. And then it applies the tenant's parser. So that way, the parser is allowed to be shared among multiple tenants that apply their certain types of rules for each of the packets. And then at the end, you end up extracting all of them into a single header where you can then pass it on to whatever specific program is either in the compute or elsewhere. Then for the control plane on the ingress and egress, so the packet flow goes from left to right, and they define a sandwich architecture. Essentially, what this means is that it first starts with the system program passing certain state. Starts with the system program passing state to tenants, sort of the link utilization or how many packets are coming. So anything that's shared and that's just general is done by the system program. Then in the middle, we apply the tenant's control logic, and this is where the tenants could do whatever they wanted to do, right? This is where they could implement the no paxos. This is where they could implement reordering of packets to achieve consistency. This is essentially where the logic, where the innovation would happen if this was possible. And then once this is complete, then the system takes over and then does the specific translations. For example, it establishes its egress ports. It makes the translations for virtual IPs to physical IPs, virtual ports, physical ports, etc. They basically define this as a write then read. It is essentially like the control plane writes stuff, which the tenant's control plane then reads and acts upon, and then the system reads that again and then writes it to a physical system state so that it can actually be used by the hardware. And then they also go into more detail with regards to the runtime memory allocator. This part I thought was clever. I got this from the presentation of the paper, which the paper did not clarify it as much, but you essentially have the one big array that contains all of the memory, and the memory allocator defines basically partitions the whole memory into different sets of one big arrays. And these config parameters basically contain basically allow you to determine where each packet lives. So and the way they do it is like, they define a virtual ID, which is the ID for each of the tenants, and then the action essentially defines the offset, and so where you start reading and the amount that is allocated per tenant. So for example, we can see that this big array, in combination with this table, we can see that tenant 1, the offset is 0, so it begins here, and then the amount is defined how much it's allocated to it. And then for v2, it says, well, this is the offset. So, the tenant would start here, and this is how much it has allocated. And everything is stored in a single register. So this is essentially the way in which they are able to partition the virtual memory among all the different tenants. And they give you an example on how they would store, for example, a physical address. They would do the metadata offset plus then reading the virtual address and the metadata amount. Then after they talk about the idea of how to enable multi-tenancy, they go and talk about their implementation. I recommend everyone that's not familiar with P4 to check it out. I wasn't, but it's P4. So they use the barefoot Tofino switch, which is a specific type of switch that's available. And they also use the P4 language, which I was not familiar with, but it's essentially a language that you can use to program these switches. And it's a pretty simple, straightforward language that some of it applies to all architectures, and it also has extensions for specific architectures that don't necessarily translate between switches. But it's relatively simple, and you're able to define you define your headers and how big the headers are. And then you can also define these things called actions that are basically applied in a specific type of order, or if a certain condition is met. So a very simple, straightforward programming language for processing packets. And basically, the way they implemented this is they have the compile time linker, and they extended the P4 compiler to be able to allocate resources to each tenant specifically. And then the runtime allocator, well, they based it off auto-generated APIs to pull records and modify the table entries, so that each tenant could have more or less memory depending on what they need or what they request. And they share some of the results. Basically, this what they say here is what you see on this graph is basically they use the system program, right, which is their basic parsing and forwarding logic. And then they also use the implementation of netcache and netchain, which are two other papers. And they packaged everything together. And what you see here is that in terms of resources, the light blue is basically the merge program. And then this other set is all of the programs separately. And what you observe in each case up until here is that the merge program uses less resources than the combination of than basically all of the programs stacked together independently. They basically add each resource utilization. And the only exception is PHV, which is the packet header vectors and the gateway tables. And the only exception here where you see a little bit more utilization on the merge program is because of the overhead that you need on the gateway tables to be able to manage the different tenants, and the packet header vectors, which is where you store the headers for all of the packets that are coming in for all of the tenants. You actually end up using a little bit more on the merged one than if you use them individually. But, well, I guess for most of it, you do see an improvement in resource utilization. And then the conclusion, well, the conclusion is they have a hybrid solution for multi-tenancy support, and then they basically need both, right? Each individual is not enough. You have the compile time linker, which is general, and you're able to define the different resources and allocate them to each tenant. And then you also have the runtime memory allocator, which is dynamic, but it's pretty limited. It really just allows you to manage the memory that's there. They also had another graph that explained the performance that had to do with the runtime memory allocator efficiency, and I didn't quite share it as much, mostly because I didn't understand it properly. But essentially, they say that their solution is more efficient than static equal allocation. And so the red one is their solution, and the blue one is static allocation. I guess what I was confused about was how they define the memory hit ratio, and then the fact that they show you the mean and the 5th percentile, as opposed to, well, I guess I was confused about doing it at 5% instead of 95th. So yeah, but essentially they say that their solution is also more efficient from a memory allocation perspective, and that's it.